Okay, so how's the project progress going?
Good.
Good. So do you guys know that the final report should be in the ASCE 7 paper format?
Yep.
So do you have a template or no? I posted a sample project report from last year. Did you guys check it out? So it's on Canvas, and I think you can follow this template, and I might post a Word template for the project report. Mainly, what I want to see is, I want to see an abstract. I'm not sure if you guys have read journal papers before, scientific journal papers. The abstract is basically you explain what you are going to do, what is the objective of what you did, and a summary of the results, like it's 200 word or something. And then an introduction, I need you to do a little bit of literature review, like about the structural systems that we discussed, the outriggers, the frames, the shear walls, what the difference between these systems, what these systems can achieve in terms of better deformation, better resistance. So maybe 1 page, 2-page introduction about the lateral load resisting system, about seismic, about tall buildings, and all these stuff. And then once you finish the introduction, you will have a section about the methodology. So what is your method? And then in the methodology, you list mainly for any tall building design project or analysis project, I need to see a full profile of the whole building. Like, don't miss that either in the presentation or in the final report. I need to see how's the building look like. I want to see how's and also the deformation. I want to see the deformation on the whole building, the drift, the total displacement. So I need to see all that. And the main result from this project, and that's the main objective of this project, should be, I want to see how the shear lag, how the total displacement, how the interstory drift are changing with the parameters that we are changing. Like we are changing the spandrel beam depth, we are changing the coupling beam depth, with the other things. Maybe you can do braces if you want to do braces for the building. So you choose, but the main thing, I want to see how the total building displacement, how the interstory drift, what else did I say? The shear lag. So you need to show me how the shear lag from the different systems look like. That's the main objective from the project. And I'm sure Ahmed showed you examples from the project last year. So you don't have to do the same thing, but I mean like very close, right? Okay, so today we are going to continue on the structure analysis part that we started last time. So last time we...
I have a question.
Sure.
For the earthquake nodes, do we choose anywhere? Because I saw it was like a specific point.
Los Angeles?
Anywhere around.
Yeah, but the thing is, Los Angeles, the whole thing is the same spectral acceleration.
Okay.
The whole city.
Thank you.
So, yeah. All right, so yes, like last week we started to talk about the method of consistent redundance, and this is one of the most important methods for structure engineers to calculate reactions for indeterminate structures. And I posted a homework, I hope you guys saw it, the deadline is this week. We are gonna have 1 or 2 small homeworks based on this lecture and the next lecture. There is lecture next Tuesday, right? Tuesday is not, so this is gonna be our last main lecture, and you are gonna have a quiz on that day on the things that we started last lecture and this lecture. This is gonna be the last quiz. We had 2 quizzes. This is gonna be our 3rd quiz. And I believe it's gonna be on the method of consistent redundant, the one that we did last week, all right? Okay, so today we are gonna talk about something that I already give you a little bit of hint about it when we did seismic, but now we are gonna do it much more in deep. So let's talk about Hooke's law. Do you guys know what Hooke's law is? Like if you have a column, and this column has a load B, and the column has a stiffness, and we always represent stiffnesses with a spring. Like if we have axial stiffness, we do like something like this, and we see this column has K. In real life, this column is not a spring, but you can represent it. We structurally represent it as a spring. So when you compress this column is gonna have like axial deformation, and it's gonna go something like this delta. And if this column stiffness is K and exposed at delta displacement, so Hooke's law says that the force, this force, the delta, the deformation that a structural element is gonna be, the deformation of a structural element is proportional to the amount of force that is exposed to, okay? And the proportionality factor is K. So this is our rule, B equal K multiplied by delta. And this should apply for anything. Axial stiffness, shear stiffness, flexural stiffness, so all these stuff. But the thing is, sometimes when it comes to bigger structure, it is not only one K. The K of the stiffness of the structure is not like single number, it's gonna be a matrix. And we're gonna see how we can convert this as a matrix. But the thing is, let's think about it, how we can reform this shape. If I have a beam, something like this, and maybe fix it here and has a bunch of load, and let's say a concentrated load, and I have a concentrated moment here, M, all right? So the thing is, based on the stiffness of this beam, by the way, this is a different concept of the stiffness here, because this was very direct. You put a load, and the column is gonna be compressed, and you have a delta. But the thing is, I wanna look at, for example, the rotation that is gonna happen here. Because the thing is, based on the stiffness of this beam, is gonna affect the rotation that is gonna happen at the joint. But not only the stiffness, also the loads. So the more loads you are gonna put here, the more rotation that you are gonna have here. So I wanna find what is the load, the total load that is gonna be here, that is gonna make this to rotate. Well, there is a direct bending moment here that can make this beam, like if I don't have this load, these two loads, the distributed and the concentrated, what is gonna happen to this beam? This beam is gonna make something, let's put it that way, right? If I don't have these two loads. But these two loads wanna do what? Wanna bring this down, right? Wanna make this like this, right? Depends on which one is bigger, and depends on the stiffness of this beam. And when I talk stiffness, and we are talking about rotation, not axial, depends on the flexural stiffness of the beam. When we say flexural stiffness, that means the moment of inertia of the beam. If the beam is really, really strong, the rotation is gonna be very small, okay? All right, so there's multiple loads here that can contribute to the rotation of this joint, right? So the way we characterize these loads, we say some of them are nodal forces, and some of them is called fixed end forces. What is the fixed end forces? I'm gonna tell you about it right now. So, but I want you to understand the difference between action and reaction. So let's say I have a beam like this, and this beam has a load W. Can you guys tell me, let's say this length is L. Do you guys know what is the reactions here? Okay.
FM equals M. I don't remember.
It's W and L. Definitely it's going to be function in W and L, right? So if we have a simple beam, what is the load in the middle? It's WL squared over 8, right? So this one, remember, it's WL squared over 12, okay? And this one is WL squared over 12. Is that reaction or action?
Reaction.
Reaction, right? This reaction is coming here because there's an action here. This action is equal to WL squared over 12, and same thing. So what happens is, this beam has a load, wanna bend that way. So there is an action, wanna bend this beam, WL squared over 12, but the support make a reaction, WL squared over 12 to resist this. But what is responsible of the deformation? Like, let's say you have a deformation, this is gonna deform something like this. The action is the one that caused the deformation. So this one is the one that brings the beam down. That's the one that makes the deformation. And the external loads, also the one like this one, is the one that makes the deformation, not the reaction, right? So what makes this green deformation is the action that comes from this load and this load, like this one, right? Because this one and this one makes a load, action here and action here, to make this deformation, not the reaction, all right? Okay, so what I want to say is the total deformation, or the total deformation means displacement and rotation. So the total rotation comes from the nodal forces and the action that comes from these loads. So if I want to find out what is the rotation here, so this should be equal to the F total that comes in from this one. Let's say it's M action, MA. And I'm gonna call this MN, the nodal moment, all right? So my load is gonna be equal to F total of both of them is gonna be equal to a stiffness matrix K. We're gonna talk about this K, but it's the same thing like here, multiplied by delta. I'm gonna put it as D because this one is rotation. This D can be delta, can be theta. That is the governing rule of the stiffness method. And the F total actually is equal to the M nodal, the force that are direct at the degree of freedom, plus the M action that comes from the other load, because these two loads make an indirect action here. But this one is direct at the node. It's not indirect. These ones are indirect because they are here, but they cause action at the node that we are looking at. And sometimes we write this in a different way. We say that the F total.
But doesn't Mn plus Ma equal 0? Because they're opposite.
No. Because this is an external load. Like can be 10, can be 100, but this one is coming from these. They are independent.
Okay.
They are not dependent. But I can say, based on what you said, I can say that here there is an M reaction here, or we call it M fixed end forces, MF. Okay, and if we want to make it general for any force, FF. All right, this FF is equal to the MA, but in a negative sign. All right, so we can write F total is equal to, I'm gonna write it in a general way, the F nodal forces plus the F action. That is a general rule. But we usually write it as F total is equal to Fn minus F fixed end forces. Rather than dealing with action, because when we solve a structure, we don't solve for actions, we solve for reactions. So we are gonna move the action to be a reaction with a negative sign. So right now, stiffness method. So right now, this is the governing rule. The F total at any node is going to be equal to a stiffness matrix multiplied by a deformation matrix, which is equivalent to this one. This one was simple because the load was just direct on an axial deformation, but if I have bending deformation, it's going to be a little bit complicated. But we can put the F total as, by the way, these vectors, but this is a matrix. So I'm gonna put this as Fn minus F fixed end forces, which is this one. And this is gonna be equal to the matrix K, and the vector of the displacement. So I can send F fixed end forces to the other side, and I can put the F nodal forces is gonna be equal to the F fixed end forces plus the stiffness matrix multiplied by the deformation D. That is the most important rule in the stiffness method. The most important one. Never forget this one. The nodal force at a node that has a degree of freedom is equal to the fixed end forces at this node multiplied by the stiffness matrix, plus the stiffness matrix multiplied by the deformation. All right. Let's apply this on a spring example. But before this, I want to talk about the this K, the stiffness matrix. We're going to talk about this concept, how we can build a stiffness matrix for an element, okay? Let's see how we can do that. So, to build a stiffness matrix for an element, think about it, this is a member, a structural member, and I want to make a stiffness matrix for this member. First, I have to look at the degrees of freedom. I put you here as steps. I'm going to write it in a little bit, but I don't want to write it now because you will not know what is going on. I need to explain it first. So I'm telling you how to build the element stiffness matrix for any structural member. I said number one, determine the degrees of freedom. Like let's say we have a bar that means it only takes axial deformation, like a truss member. The truss member, and for springs, let's talk about springs, not bar, because the truss, you have two here and two here, right? It can move X and can move Y. For springs, it's usually one. One here and one here, because the spring only get compressed, cannot get any force like this. So number one, determine the degrees of freedom, okay? And number two, I said restrain all the degrees of freedom of the element. Number three, assign unit deformation at each degree of freedom. And number four, construct an end-to-end matrix for the element. So if I wrote this on the board, you will not understand, but let me do something else. Once I put it, you are gonna follow what I'm doing step by step. So let's say the first step, I have a spring like this, has a stiffness K, and I wanna find the stiffness matrix of this spring. Okay? So, verse number one, determine the degrees of freedom. So the degrees of freedom, since this is spring, I know that this point can move that way, U1, and this point can move U2. That's number one. Degrees of freedom. And the degrees of freedom, U1 and U2. You will tell me, how about in the other direction? Yeah, it can be there, but the thing is the spring is not going to have any deformation in the other direction, only have axial deformation. Okay, so I have U1 and U2, these are the degrees of freedom. Then number two, restrain all degrees of freedom. Like take this spring, like this, and restrain all the degrees of freedom. Make this spring not to move. That means you fix this and you fix this so the spring cannot have any deformation. Number three, apply unit deformation at each degrees of freedom, one at a time. All right. So one at a time. So I will take U1, and I'm gonna hold this support and compress this support all the way inside, and make a U1 here, while U2 equal to 0. So apply unit deformation at each degrees of freedom, one at a time. So I'm gonna make U1 equal to 1. Why I do this? Because the thing is, all right, so I'm gonna tell you why I'm making all that. I don't know what is the value of K, right? That's what I want to find out. I want to find the value of K. The thing is, we manipulate a little bit the whole thing here. We say, I know that B equal K multiplied by delta. What if I put delta equal to 1, so B is going to be equal to K? If I found the value of B, so I found the value of K. So that's what we are doing here. We put a unit deformation, and then find the external, the forces, and if we find the forces is going to be equal to K, right? All right, so that's what we are doing here. So I fix U2 and I apply unit force at 1 and see how my structure is going to respond, okay? And then here I put U1 equal to 0 in a separate structure, and I apply U2 equal to 1. Usually, the element the stiffness matrix is n by n. It's a square matrix. And n is equal to the degrees of freedom. So I have 2 degrees of freedom here, so this is 2 by 2. And the stiffness matrix is going to be something like this: K11, K1, 2. And this is gonna be K2, 1 and K2, 2. So here's 1 and 1, the first row, and the second row is gonna have 2. The more that you move columns, the columns is, so this is the row number, the second is the column number. So this is row number 1, column number 2. I put here, let me write it. Okay, let's leave it in a little bit. All right, so I put U1 equal to 1, and you know that this is, the spring has a K stiffness. So let me put K on every one of them. This is K, and this is K, and this is K. So right now I want to find the forces because I told you if I find the force, that means that I found the stiffness. So you tell me, if you apply unit deformation and here is K, what is the force that I need here to make a unit deformation? What is the force B here? The force B here is the deformation multiplied by K. So you are going to have a K here.
Wow.
And how about here? What is the reaction that you're going to have here?
Oh, K again?
K2, because 1 multiplied by K is equal to K. So this is going to be K because there's the only way to make a unit deformation here is to apply a force B equal to K. Same thing here. What is the force that I need here to make a unit deformation?
K.
K. What is the reaction it's going to have in here? Because this support is fixed. It's not gonna, never going to move.
K.
It's going to have K. So we call this part is K11. We call this part is K12. We call this part is K21, and this part is K22. So let's put it here. I'm gonna put the K. Let's say K21. K21, the 2 means the unit deformation is at point 2 or at U2, right? 1 is the U1, like the deformation at U1. Let me, due to unit deformation at
Point. Support.
stiffness force at point 2. Okay, I said unit deformation. I said here stiffness force. It's the same thing. This is the stiffness force or the unit deformation at point 2, and this is mean the point that I'm looking at because this is still point number 1. This is still point number 2. So here I'm saying due to unit deformation at point 1. I think this one is not right. So I'm gonna change it. So let's say this is the point 1. So what K21 means? That means that 2 is the unit load or the unit deformation is at 2. 1 is the point that I'm looking at. Let's say this one, K12. So this is the unit deformation is at 1, but I'm looking at point 2. So my stiffness matrix here is gonna be, look at that. K11 is equal to
K.
K12,
0.
K12.
Oh shoot.
Is negative K. Why it's negative? Because it's in the opposite direction of the assumed degrees of freedom.
That's true.
So the degree of freedom is that way, this is that way. How about this one?
Negative K.
So this is gonna be negative K,
K.
K. So usually the stiffness matrix of any member, the diagonal is always positive. Diagonal is always positive. Because there's no way that you are gonna apply, that you are gonna assume that this point is gonna move U1 and the force that is gonna make U1 is in the opposite direction, right? Because if U1 that way, so you need to apply force in the same direction of the displacement, okay?
I don't understand the point of putting the U2 equals 0. It's just gonna equal like negative K. Like I don't understand that.
All right, okay, so let's say this is my spring. I fix it both too. Like there's no way that this spring is gonna have any forces internally unless I move the support.
Yeah.
So what I do is I take this support and I move it unit deformation while I'm fixing this. That means that the U here is 0. Like this point is never gonna move. So that means this is fixed. But here I hold the support and I move it 1. once I do this, I need a force equal to K multiplied by delta. So K multiplied by 1 is going to be K. So you need a force equal to K here. And once you apply this support never going to move. So it's going to respond with a reaction in the other direction. So if we did the same thing here, you take the support that way, this one is going to have tension. So what happens here, this is going to have compression force, this is going to have a tension force.
Okay.
All right, so this is the stiffness matrix. Right now, you know how to develop a stiffness matrix for a structure. This is a general steps, and I put the steps here like this. I told you, determine the degrees of freedom, restrain all the degrees of freedom, and that's what I did here. I restrained them. Assign unit deformation at each degree of freedom, one at a time, and then calculate the fixed end forces. So what I did, I applied unit displacement, and I calculated the fixed end forces. This is called fixed end forces because they are fixed. And then I said construct the stiffness matrix n by n, and then the fixed end force vector. We're going to talk about the fixed end force vector in a little bit. But this, how to get to K. So let's solve a problem and see how we can do that.
What happens if you make U2 go the other? Is that incorrect? If you make it go the other way?
If you assume U2 from first place, you can assume that
you assume U1 goes this way, U2 goes this way, so they go towards each other? Like
you can
without
assume that from first place, but when you apply the forces, you have to apply the forces in the same degrees, in the same direction of the degree of freedom. Like if you assume that U2 is going that way, you apply the force here, the unit displacement going in the same direction of the degree of freedom. But usually we have, when we develop a stiffness matrix for a structure, we have a convention, we have a rule. There's a positive, like, I'm doing this because that's actually what SAP 2000 do. SAP 2000 solve using the stiffness method. Once you build your structure, he make each element separately and build the stiffness matrix for each element, and then build the structural stiffness matrix. And there is a rule for the degrees of freedom. Usually the positive is going that way, the negative is going the other way. And if it's a frame, usually it's going to be something. This is the positive, positive, positive. Other than that is negative.
Got it.
You can assume the other direction, but that's what the community of structural engineering agreed on. Okay, so let's solve an example and see how we can solve it using the stiffness method. Okay, so I'm gonna put, all right, I have all right, I told you this is a rigid body and it's constrained top and bottom. That means that this rigid body only allowed to move that way. There's no way it's gonna go up. There's no way it's gonna rotate, all right? And you have 3 springs. The stiffness of each spring is equal to K, all right? And you start pushing up and down with a force 10 ton. And I'm asking you, find the deformation of this body. That means I want you to tell me if I apply 20 ton, 10 and 10, how much displacement this body's gonna have. Definitely this body's gonna move that way, right? It's not gonna move that other way, yeah.
Are you saying they all have the same K?
Every one of these have the same K. Yeah, this is K, let's say 1,000, 1,000, 1,000. All right, so that's number 1. I want you to find the displacement. And the second one, I want you to find the force of each one of these springs. Before solving this problem, let me put here example. And I'm asking you, number 1, to find the displacement, D, and number 2, find the force in each member, okay? All right, can you guys tell me before I solve this problem, what is the solution? Can we do that?
20 over 3k. 20 over 3k.
Excellent. Why?
Because you have p equals p delta. So you divide by k, you get delta.
So why the 3K?
Because they're all the same and all going in
Because
the
they
same
are
direction.
in
The same
barrel,
direction.
right? So the thing is, right now you only have one delta. So all these springs are gonna have the same delta. Some of them are gonna be in compression, some of them are gonna be in tension, right? So this is, which one is gonna be in tension?
The k.
This one.
That low.
And this is gonna be, but they all are gonna have the same force, right? Two of them are gonna be in compression under the same force here in tension, right? And they are all in barrels, so the total stiffness of this structure is 3K. Do you guys remember when we have a barrel springs, it's gonna be K plus K plus K. So 3K, that's the total stiffness. And the total force in the direction of the movement is 20. So basically you are gonna do, say, P equal K multiplied by delta. So I know that the total is 3K, and I know that B is equal to 20, because I have 10 and 10. Maybe they are distributed differently, but they are serving the same purpose, moving this in the same direction. So delta is gonna be equal to 20 over 3K. That is the total delta. Let's see how we can solve this using the stiffness method. We are gonna take a long time, but we are gonna learn something. Because sometimes this is gonna be big and we will know how to solve it, like, visually. Okay, so verse little by little. Number one, the degrees of freedom. How many degrees of freedom I have here?
3.
How many degrees of freedom do I have here? You just get one delta here, right? You didn't get 3 delta. So you only have U1, because this one is only can move here. There's no other degrees of freedom. It's not gonna rotate, it's not gonna go up and down. This body, like if, I'm gonna put it here,
That's true, that's true.
here, 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 this body only allowed to move U1. There is no other thing. This one and this one are gonna be the same like this one. Yeah, you can say, oh, it's a 3, I have 1, 2, and 3, but the thing is they are equal to each other. Unless there's something going here. This body can make like this. Now we have 3.
Why did that one have 2?
This is a member. Right now I'm talking about a structure. So I'm gonna tell you right now, if you take this member alone, we are looking at the degrees of freedom if this member is free. So that's what I did here in a member stiffness matrix. I'm gonna tell you how we can get from the member stiffness matrix or the member degrees of freedom to the structural degree of freedom. So the thing is, we take this member separately to study how the stiffness matrix in general look like. But is this member in this structure is gonna be free? We assumed here it's a free, all right? But here it's not free. Here it's a free from this end, but it's not free from this end. So we will find a way how we can make this fit into this. Right now, we are in a structural degrees of freedom, not at member degrees of freedom. So the structural degrees of freedom here is U1 in this direction. Okay, so I have U1. Number 2, I want to build the structural stiffness matrix. But, okay, okay, I'm gonna make the node, because this is a nodal force. We're gonna talk about the nodal force in a little bit. So let's say structure, stiffness matrix. I talked here about an element stiffness matrix, but I'm gonna tell you how SAP 2000 collect the stiffness matrix of the element and make the structural stiffness matrix. All right, so first you have to put the element stiffness matrix element by element. So I'm gonna call this element number 1, this is 2, and this is 3. By the way, the springs, this is the general stiffness matrix of the spring. If this is 3K, so this is gonna be 3K, negative 3K, negative 3K, 3K. If this is 100, you're gonna multiply by 100. So since I have all the same, so the K of member number 1 is gonna be K, negative K, negative K, K. K number 2 is gonna be K, negative K, negative K, K. Member number 3 K, negative K, negative K, K. All right. Okay, so that is the stiffness matrix of a member, assuming that both points are free, right? But in this structure, are they free? They are not free. It's a free from one end. So which end here is free? Is the end number? Look, this is U1 and U2.
U1. Well, U2 is free.
U2 is the one that's free. So that's what we do. Because this column is coming,
U1.
this is gonna be 0, and this is the one that have U1. Look at that.
What?
Why did I do this? This U1 and U2, if it's an element, but here U1 means my degree of freedom here.
True.
So U1 of the, let me write it in a different way.
Yeah, like point 1 of the member is the fixed, point 2 is...
Exactly, so here's U1 of the member is equal to 0, and U2 here is equal to U1, all right? So what did I do here? This is U1 and U2 of the member, but here I'm looking at the structural stiffness matrix. U1 is opposite to which one of these?
U2.
It's U2, right? So I put here that this column is coming from if U2 is free. But this one is not free, so I have to fix this degree of freedom. So that's why I put 0 and U1. And actually you can do it on the rows. Like you can say, this row is 0, and this row has a U1. How about this one? This one has the degree of freedom on the left end, right? So this is the opposite. You are gonna have U1 here and 0 here, because this one doesn't have any degrees of freedom. So you can do the same thing, U1 and 0. Same thing here. You're gonna have U1, 0, U1, 0. Why do I do that? The thing is, the way that we build the stiffness matrix of an element, we assume that all points are free, okay? But in real life, they are not gonna be free. But we build it that way, and then we make zeros at the areas that doesn't have degrees of freedom. Like here, this is stiffness matrix of a free member. And this actually, unstable structure, right? If this member is in the air, that means every point can move, that's not a structure, okay? But this is how we build a stiffness matrix. Once we fit this stiffness matrix in a structure, we put zeros at the points that doesn't have a degree of freedom. So since this point doesn't have a degree of freedom, so I put 0, and then we cancel these stiffnesses. And I cancel all the one that have zeros,
Wait,
and all the one that has zeros.
That one was the other way around.
Oh yeah, sorry. This is the one that has zeros. K and K. Yeah.
U1.
So I cancel the one that has zeros because they don't have a degree of freedom, right? So I get left with a K here, and a K here, and a K here. So if you want to find the total stiffness that contributes to the deformation U1, and since you only have 1 degree of freedom, so your matrix is going to be 1 by 1, there's only one number, so the structure stiffness matrix is going to be equal to K plus K plus K. So that is equal to 3K. And that's actually what we find out a few minutes ago, that they are all in parallel, and if you want to find the total stiffness, you are gonna do K plus K plus K. All right? So that is the structural stiffness matrix. Okay? Does anybody have any question?
So,
The concept is a little bit hard, a little bit confusing, but this is how we build the structural stiffness matrix. Look at that. This one, you cannot solve a structure like this with all degrees of freedom at all ends. We build it free, and then when we know that these degrees of freedoms are not degree of freedom, are fixed or cannot move within the structure, we zeros all the or the columns and the rows that comes from this fixed degree of freedom. Yeah, I have a question.
I understand how the first column and the second column, like the first column corresponds to one end of the member, the second to, but how do the rows?
It's the same.
correspond?
The stiffness matrix of a structure is symmetric. Like, look at that. This is gonna be negative K, and this is gonna be negative K. Like this or this. So you have a U1 here, and U2 here. If U2 is equal to 0, so this is also U1 and U2. So they get canceled too. All right. So
But shouldn't the K, like for example, up in that one, the K up top, the negative K, shouldn't that correspond to U1? That one, yeah. Shouldn't that correspond to U1? In the vertical sense, but then it doesn't in the horizontal sense, I guess.
Okay, so well, let's take it step by step. So let's say, for example, this column K11, or this row, for example. This row is coming from, if you have a degree of freedom here, like U1, and you have a 0 here, so this one is never gonna move in real life. So if this is fixed, it's never gonna move.
Yep.
So you only have, for example, a degree of freedom here. So you're only gonna end up with having this column. So that's why we cancel all these. I'm gonna show it on a bigger structure, and maybe you are gonna understand it that way. Okay, but let's finish that one first. I got the 3K, right? So the thing is, I don't want to find the stiffness matrix of the structure. I want to find the total delta that this structure is going to have. This is going to be really easy, because once you find the stiffness matrix of the structure, you are going to apply the rule that says, the one that we had it boxed here, the F nodal is equal to the F fixed end forces plus the stiffness matrix of the structure multiplied by D. So F nodal that I have 10 and 10, that's the nodal forces that are directly applied at the degrees of freedom. So this is gonna be 10 plus 10. I don't have any fixed end forces. Fixed end forces equal to 0, and I'm gonna show you another example that has fixed end forces. Plus the stiffness matrix of the structure is equal to 3K multiplied by the displacement that I'm looking for. That's what I'm looking for. So D is going to be equal to 20 over 3K. That's 20, that's a 3K, that's 0. I divide over 3K, so the total displacement at this point is going to be equal to 20 over 3. So U1 is equal to 20 over 3K. All right, so I found U1. It's exactly the same way that we did it before. I mean, like, we found that these are barrels, 3K, and I have 20, so it's gonna be 20 over 3K. But this is with the matrix equation. What if I wanna find the force in each one of these springs? Can you guys tell me what is the force in each one of these springs without any calculations? This one is tension or compression?
Tension.
What is the value of this tension? If you know that
20
this
over 3.
20 over 3, right? Because the whole 20 force is gonna be distributed 1/3, 1/3, 1/3, right? But let's actually solve this using the stiffness method. If you wanna find the force of any member, F member number 1 is gonna be equal to F fixed in force, which is 0, plus the stiffness matrix of the member. By the way, this is a structure. Right now we are talking member, multiplied by the U or D at this member. Okay, so all this is matrices and vectors. So this is 0. This is what I'm looking for. F member number 1 is gonna be equal to 0. What the 2 zeros mean? The 2 zeros means, like, if this is the spring, I'm looking for the force here and the force here. The two forces, number 1 and number 2. Plus the stiffness matrix of the member number 1. This is the stiffness matrix of member number 1. K, negative K, negative K, K. Multiplied by the displacement at member number 1. What is the displacement here? 0. What is the displacement here? U1. So 0, and I have here 20 over 3K. So let's do that. Can you guys multiply matrices? So you multiply this row by this column. So K by 0, 0. Negative K multiplied by 20 over 3K, negative 20 over 3. This one, negative K 0, K, you are going to have 20 over 3. So that means that the force here is not that way. It's in the opposite direction, and it's equal to 20 over 3 because it's negative. This one is that way, and it's 20 over 3. That makes sense. Because once you pull that one, you need the force of 20 over 3, and you're going to have a reaction in the other direction. let's get force number 2. F member 2 is going to be equal to the fixed end forces plus the stiffness matrix plus the displacement vector. So zeros plus K negative K
Less.
plus U. Alright, so the displacement of member number 2, can you guys tell me what is the U here?
1. U1.
U1, which is
20 over 3.
20 over 3K. How about the displacement here?
0.
0. So K multiplied by 20 over, so you are going to have 20 over 3,
Negative
and this
20.
one is going to have negative 20 over 3. So once you put the forces on this spring, so you are going to have 20 positive over 3, and this one you are going to have a reaction 20 over 3. Alright? So look, actually we can solve this visually from first place, like without doing all that. Like we found out that this is going to be 20 over 3K, and then you multiply this by K, so it's going to be 20 over 3, but this is how you solve it mathematically using the stiffness method. So let's actually make this complicated that we cannot solve it visually. So let's see how this. All right, so I give you these springs. These springs are bare or series? Series, right? The thing is, I can't, this is 2 degrees of freedom. I will not be able to solve it visually. So we need to use the method of stiffness to solve this problem. Look, this problem has how many degrees of freedom? The structural degrees of freedom. By the way, this, you cannot say these are degrees of freedom. This is just something to build the stiffness matrix of the element. So this is something locally to tell you how this stiffness matrix comes from. And when it comes to a structural degrees of freedom, we make zeros at the degrees of freedoms that are not moving. So here I'm asking about what is the structural degrees of freedom? How many degrees of freedom that this structure has?
1.
Where's this one? This one or this one? It's 2. Because this is the points I have.
Oh,
this
because
point
they move
is not a
separate.
degree of freedom. This one, the degrees of freedom is at the points that are separated. If you have, like, if you can make these 2 springs one spring, and you can find the resultant of both of them and make them one spring, you can have 1 degree of freedom. But since they are separate, so sometimes we have a problem like this. You have 2 springs like this and 2 springs like this, and they are connected with 1 spring like that. So sometimes I know that the springs in parallel are very easy. If this is K and this is 2K, I can make the equivalent of both of them 3K and deal with 1 spring, right? but this is not the case. I have these springs separate, so I have this as, I'm gonna assume that I have U1 here and U2 here. So I have U1 and U2. These are the 2 degrees of freedom. This is step number 1. Step number 2 is to find the fixed end forces. Here in this problem, I didn't have fixed end forces, but in this problem, I have fixed end forces, and I'm gonna tell you why. Fixed end forces and nodal forces. By the way, nodal forces, I mean like the force that apply directly at the degrees of freedom, and the F nodal that we have here was 10 plus 10 equal to 20. But because it was 1, we put 10 right away here, 10 plus 10. That's the nodal forces. But here it's easy, like you guys can tell me, what is the nodal forces? F nodal. F nodal is a vector, has a number of rows equal to the number of degrees of freedom. So if you have 2 degrees of freedom, so it's gonna have 2 numbers. This number is the nodal force at degree of freedom number 1. This number is the nodal force at degree of freedom number 2. Can you tell me what is the force that are directly applied at the degree of freedom number 1?
20.
It's 20, but it's in the opposite direction of U1, so I'm gonna put negative 20 because it goes that way. U2 is that way and 100 is that way, so this is gonna be 100. That is called nodal vector, okay? Or nodal force vector, okay? How about the fixed end force? The thing is, I have, what are these? 2 centimeter and 1 centimeter. This is, by the way, settlement, when settlement happen in the structure, that's a load. Because load sometimes can be direct, a force, and sometimes can be a settlement, like your foundation is gonna go, it's something like, rather than giving you the load directly, I'm gonna take the whole foundation down. To take the 2 centimeter down, like, there's definitely a force that caused these 2 centimeters. So I'm gonna convert these 2 centimeter as a fixed end forces to find this vector, because if you guys remember, our rule is F nodal vector is equal to F fixed end forces vector plus the stiffness matrix multiplied by the displacement, right?
Yeah.
Okay, so let's see how these 1 centimeter is gonna do. So the way that we handle it, we fix all the degrees of freedom. So this is gonna be something like this. Or like that. And I have K, 3K, 2K. And once I fix all the degrees of freedom, I apply 2 centimeter here and 1 centimeter here. So now I want to try to find out how much of force I need here to move this point 2 centimeter. Can you guys tell me?
K.
This point to move 2 centimeter, how much force do I need?
P or K, whatever load.
K multiplied by delta, right? So
Oh, how
this
much
K
force
multiplied
I
by the
need.
2 centimeters.
Yeah,
So
yeah.
K delta is going to be 1,000 multiplied by 0.02. So it's going to give you 20. But definitely this is going to trigger reaction on the other side is going to be equal to another 20. How about this one? I need a force that way. It's going to be equal to
2 times 1,000.
2K,
2,000.
2,000 multiplied by 0.01. So it's going to be 20. And here you are going to trigger another reaction equal to 20. How about this one? Does it have any, because there's no settlement. I didn't apply any displacement at these ones. So I have 0 and 0. So to have the fixed end forces at the degrees of freedom, I want to build another vector, FF. And I'm going to have 2 components here, which is the fixed end force at the degree of freedom. This, I don't care about this. I only care about how much this displacement is gonna trigger a force at the degree of freedom. So this one is triggering negative 20 in the opposite direction of U1. So this is gonna be equal to negative 20. How about the other one is gonna be also negative 20. By the way, we can find this in a different way. You can find the fixed end force of member number 1. So you can say negative 20 20 minus negative 20. That's fixed end force for member number 1. Fixed end force for member number 2 is going to be 0 and 0. So I'm going to put 0 and 0. Fixed end force for member number 3 is going to be negative 20 plus 20. So I can say negative 20, and this is 20. And then you try to locate the degrees of freedom of the structure in the element. This element doesn't have any degrees of freedom in the structure, so I put 0 here. But this has U1, so I put U1 here. So I don't care about this number. Then this has U1 and U2. This has U2 here, opposite to this one, but this one doesn't have a degree of freedom, so I'm gonna put 0. So this, I don't care about it. And you start to sum the numbers, U1 plus U1. So negative 20 plus 0, I'm gonna put negative 20 here. And then 0, because this is U2, plus negative 20, so you're gonna have negative 20 here. So there's different ways to do it. You can do it right away, and you can get each member separately and sum all of them together.
Why is F20 low?
Because this one doesn't have any displacement. This member, we already included the forces on this member, the 20 and the 100, already in the nodal forces. Okay. Actually, you can make the fixed end forces a nodal force, but you have to opposite the sign, because do you guys remember action-reaction thing?
Yes.
So you can do the same thing. But right now, we need everything organized.
Yeah.
Okay. With this, let's move to the next step. We found the fixed end forces, we found the nodal forces. By the way, all what we do, we are trying to find the component of this equation. We find F nodal, we find F fixed end forces. Now I want to find the structure stiffness matrix, S. And to find S, I need to find each one of these separately. So, number 3, structure stiffness matrix. All right, to build a structure stiffness matrix, I need the element stiffness matrix one by one. I have number 1K, so this is K, negative K, negative K, K. K2 is going to be 3K, negative 3K, negative 3K, and 3K. K3 is going to be 2K, negative 2K, negative 2K, and 2K. Does we agree on this? That is the stiffness matrix of an element. If it's 100K, so you are going to multiply the whole thing by 100.
Quick question. So the only reason we have fixed end forces here is because there's
Displacement.
displacement at
Yeah.
the end.
Exactly. The thing is, they are not direct nodal forces. All what I'm interested in is the forces here. But this is a displacement force that is going to affect here. So that's why I got the fixed end forces and try to find how these fixed end forces at each member is going to impact the force at each one of these degrees of freedom. Okay, so can you guys tell me which one of these that has degrees of freedom? So this is member number 1. Do I have degree of freedom here?
No.
So I'm gonna have 0. Do I have degree of freedom here?
Yes.
I have U1. And you can do the same here, 0 and U1. So member number 2, I have U1 and U2. So this is U1, U2, and I can put here U1 and U2. Member number 3, I have U2 here, but I have 0 here. U2 and 0. So we are gonna cross the zeros where we do not have degree of freedom, so I'm gonna cross this row. This whole matrix is gonna stay. This one is gonna be crossed. So what is gonna happen now? I'm gonna have a structure stiffness matrix that I'm gonna sum everyone that has U11. So U11 here is gonna be plus with U11 here. So this is this and this, they are all U1. So I'm gonna have here K plus 3K. How about U12? U12 is gonna be this one, and it's alone because there's nothing that we can plus it with. So negative 3K, and you are gonna have the same thing here, U21, negative 3K. And this one, you have U22, and you have U22 from here. So you're gonna have 3K plus 2K. This is actually something like this. You put a matrix with another matrix with another matrix. So this one, you are gonna have the U11, and this is the U12, U21, U22. And this is where the degrees of freedom is, because here is zeros. All right? If you have a bigger structure, they are gonna bunch of matrix that are connected to each other. Like if you have 10, so you're gonna have one here, and a one here, and a one here, and they are all intersected at some point. All right, so the structure stiffness matrix is gonna be equal to 4K, negative 3K, negative 3K, and you're gonna have 5K. All right, so right now I have Fn and I have Ff and I have S. I'm ready to get the displacement. So all what I have to do, I have to build these one element by element. So Fn is equal to negative 20 and 100. And the fixed end forces, as far as I remember, negative 20 and negative 20.
Correct.
And then S is going to be 4K, negative 3K, 3K and 5K. And then I have here U1 and U2. You use your calculator and solve two equations and two unknowns. And then you are going to find U1 and U2. So once you use your calculator, you guys know how to do this on calculator, right? So you're going to find out that U1 is equal to 0.033 and this one is 0.044. All right, this is not what I'm asking this problem. I'm asking to find the forces in the springs, but I cannot find the forces in the springs unless I found the deformation. So let's find the forces in the springs the same way that we did in the previous problem. So let's say member number 1, F member number 1 is gonna be equal to, I'm gonna put the general, let's put the general rule. F at any member N is gonna equal to the F fixed end forces in member number N plus the stiffness matrix of this member plus the deformation at this member, Kn. And this is something like this. So F member 1 is gonna be equal to F fixed end forces of 1. This is the F fixed end forces of 1, 20 and 20. So you're gonna have 20 and negative 20 plus the stiffness matrix of 1. This is the stiffness matrix of 1. You are gonna have 1,000, negative 1,000, negative 1,000, and 1,000. All right, how about you? This member has 0 deformation here, so I'm gonna put 0 here. But it has U1 at the other end, and I already got U1 is equal to 0.033, and then you find what is the value of the force. Same thing, F member number 2 is gonna be equal to the fixed end forces of F member number 2, which is zeros. There is no, and the stiffness are 3,000, negative 3,000. And the deformation, I have U1 0.033 and U2 which is 0.044. And then I find what is the value is. And then F member number 3 is gonna be the fixed end forces of 3, which is negative 20 and 20, plus the stiffness matrix 2,000, negative 2,000 and 2,000, and all this multiplied by the degree of freedom number 1, like at the first end, which is U2, we got it 0.044, and the other end doesn't have any degrees of freedom. And I try to find what is the final value. You guys got that? So basically, fixed end forces, stiffness matrix of the member multiplied by the deformation. This is 0 because this member doesn't have any deformation here. You should get 0 force. You should get 0 deformation here. Okay, so once you solve this, you are gonna find out that you are gonna have here negative 13 and 13. And here is negative 33 and positive 33. And here is 68 and negative 68. So you're gonna have your spring like this. Negative 13, that means something like this. Negative 13 and 13. So if you want the steps, and that's what I recommend when you solve, because you are going to have one of these in the midterm, the final exam. So the first thing you do is, for solving stiffness method, number of degrees of freedom. Okay, so you need to find what is the total number of degrees of freedom. And the best way to do it, you number the members and the joints. Like, try to say this is spring number 1, 2, 3, so that every one of these represent a member, so you don't get confused. So I'm gonna say, for example, that's what I put. I put this is number 1, number 2, number 3, and then try to find the degrees of freedom. Once you find the degrees of freedom, find the nodal forces, then find the fixed end forces, build the structure stiffness matrix. After building the element stiffness matrix, the easiest part in these sprints is to build the element stiffness matrix. It's a K negative K negative K K. That's it. You do them one by one and lay out the degrees of freedom on each one of them. All right? Okay, so once you build a structure stiffness matrix, use the stiffness method equation, this equation, substitute with the fixed end forces, this one. Substitute with the fixed end forces, the nodal forces, the structure stiffness matrix, find the deformation at the degrees of freedom, U1 and U2. Once you find the deformation at the degrees of freedom, find the forces on each member by substituting in the element stiffness equation. So this is the structure stiffness equation. This one, F nodal equal to F fixed end forces plus S matrix multiplied by the U matrix. This is this one. I got the nodal forces, which in the first step, and the fixed end forces, and the structure stiffness matrix, and then I solved this one. Okay? Once you find U, you can substitute here. So you put the U's here, but pay attention, because the thing is, when it comes to elements, the elements sometimes have a degree of freedom at an end and 0 at another end. This end has 0 degrees of freedom, but this one has a degree of freedom. So did you guys get that?
Yeah.
All right, so try to practice, because this is gonna be 25 points in the midterm. So we got 25 points the last lecture, and this is another 25 points. I put here all the steps. And when you solve this problem, try to number the steps so that you get points while you're solving. If you messed up, you're really getting points. And I'm gonna slash out, like, if you get this step wrong, so you lose just 2 or 3 points. And when you continue and you do the whole steps, you are gonna get the rest of the points. Okay? All right, sounds great. See you guys on Thursday.
Thank you.
I'm gonna assign a new homework, 3 problems, the stiffness problems to practice. So.